Welcome to Study Loop.
This is chapter 27, problem number 26. We're given a lithium ion accelerated through a potential, and it enters, after it's accelerated to a certain speed, it enters a magnetic field, a region where there is a magnetic field, and we're asked to calculate the radius of the circular path that the magnetic field is going to cause. So we have, if it's an ion for a charge, we're talking about positive E, right? It's 1.6 times 10 to the power of negative 19 coulombs. And also the mass is given to us. Excuse me. So it's given as 1.16 times 10 to the power of negative 26 kilograms. And this particle is accelerated through a potential difference. So then we know that the potential energy in terms of the potential difference, V here, is Q times V. In our case, it's going to be E times V. And this potential energy is going to be converted into the kinetic energy, 1/2 mv squared, right? So if you want to isolate V out of this equation, what we have is 2 times EV, this capital V stands for the potential, divided by the mass and square root of everything. And now after the ion reaches this certain speed, it is actually entering an external magnetic field. So the external magnetic field is going to exert a magnetic force on it in the magnitude of QVB, this V being the speed, right? So this is going to be equal to mv squared over r, r being the radius of the circular path, and this is exactly what we're looking for. So then if we isolate r out of this equation, then we have m times v over q times b. Our q being plus e and positive e, and then our velocity being square root of 2ev over m. If we plug everything in here, we're going to have m over e times b times 2e capital V over m. Now we cancel out these two, and then we cancel out these two. Then what we have is basically 2mv over e times 1 over b. 1 over b, this term is out of the square root. Now, if you plug everything here, 2 times the mass is given to us as 1.16 times 10 to the power of negative 26 times 220, this is the potential, over 1.6 times 10 to the power of negative 19 for the charge of the ion, or 1 over 0.874, which is the magnitude of the magnetic field that is given to us. So if you do this calculation, what we get here is 1.648 millimeters. This would be the radius of the circular path.